Hi, everyone. Welcome to the online causal inference seminar. Today, we have the pleasure of hearing a talk by Jin Tian from Iowa State University on estimating identifiable causal effects through double machine learning, graph-based and data-driven approaches. Our discussant today will be Ilya Shpitser from Johns Hopkins University. And in the Q&A, we have Yonghan Jung from Purdue University, who will be answering some of your questions there. So for questions, I will hand you over to Dominic, who will explain how that will work today.
Thank you, Emma. So today we're trying something slightly different. So first of all, as usual, you can submit your question in Q&A, and we have a collaborator there helping you answer it there. The other thing that we're going to do is you can also directly raise your hand. And if you raise your hand, I will try to unmute you at the next break. Like just as a warning, if too many people raise their hand, I will not be able to unmute everyone. So just a selection, but yeah, we'll try that. With that, let me hand over to Jin. Thank you for being here, and the stage is yours.
Okay, let me share my screen. Can you see it?
Yep, looks great.
Yep.
Okay, first thank the organizers for giving me this opportunity. Today I will be talking about estimating identifiable causal effects through double machine learning. So this is joint work with Yonghan Jun and Ilya. Particularly, Yonghan did the most work, including preparing the slides. So I'll be talking about estimating causal effects. That is how the outcome Y will change if we take an action on X. Formally, the probability of Y given to X. Specifically, we are interested in estimating causal effect from purely non-experimental data. This is one of the major tasks in empirical sciences, since experiments are usually costly, may be unethical, and often not feasible. In this talk, I will be talking about two scenarios. The first one, in addition to observational data, I will assume we have some qualitative causal assumptions in the form of a causal graph. And I will call this scenario a graph-based approach. In the second scenario, we're just going to assume we only have observational data. In this case, the rough idea is we are going to run a causal discovery algorithm to attempting to learn a causal graph. But normally, we will not be able to learn the unique underlying true causal graph. Instead, we may be able to learn a Markov equivalent class of the causal graphs. So in the second scenario, I will discuss how to estimate causal effect given Markov equivalent class of causal graphs. Some background. So we are going to assume that the underlying model is a structural causal model, or SCM. Normally, we will not know the SCM, but some qualitative assumptions about the SCM might be captured by a causal graph. A causal graph is a directed acyclic graph with bidirected edges. So these bidirected edges here represent unmeasured confounders. And we have that the joint distribution will factorize according to the Markov properties of the graph. For example, for this graph, well, it's known as a napkin graph by Per. So I will call this graph the napkin graph. So that's the factorization according to the napkin graph. Then the observed distribution can be obtained by marginalizing out the unobserved variables. the effect of do intervention on X is defined by basically removing this corresponding factor for X and assume X to be constant in all the other places. So this formally represents the causal effect of do X on other variables. In the first scenario, I'm going to assume that we know such a causal graph. So based on our, say, causal knowledge about the domain. And additionally, we assume we know the precise observational distribution. If we know this distribution, we ask, is a target causal effect probability Y given to X? Is it uniquely computable from PV? This problem is known as the causal effect identification problem. So here, if effect is deemed unidentifiable, it basically means there might exist two underlying SCMs such that they agree on the observed distribution, but they disagree on the causal effects, which means even if you collect the infinite amount of observational data, you will not be able to compute the causal effect. On the other hand, if the causal effect is identifiable, then we can express it in terms of the joint distribution. For example, in the mapping graph, given this graph, we may ask, is the effect of X on Y uniquely identified from the observed distribution over X, Y, and WR? Now, the causal effect identification problem has been extensively studied since the 1990s. So currently, there exists a complete and sound and complete identification algorithm. I will call this algorithm the ID algorithm. So it's sound and complete in the sense that if a causal effect is identifiable, like in this model, then the ID algorithm will express the effect in terms of distribution. If the effect is not identifiable, the ID algorithm will just output no. So it's complete in this sense. Now, in the identification results, we assume we know the precise joint distribution. Here, we are concerned with estimating the identified distribution from the data samples drawn from the distribution. So we are concerned with the estimation problem. For example, in this mapping graph, the ID algorithm might output this expression. So then we are interested in estimating this expression from finite samples. To our best knowledge, in general, for arbitrary identifiable causal effects, for some arbitrary causal functionals, the only general purpose algorithm available is the plug-in estimator. In the plug-in estimator, we estimate each conditional distributions. So they are called nuisances functions. We estimate those nuisances using some parametric model. Then we plug in into the expression and estimate the causal effect. Now, this is okay for the low dimensional data. Here, we'll be concerned with high dimensional data if we have many variables in the model. Or for this particular case, if we say W is a high dimension. And then plug-in estimators have various issues. So we would like to design estimators that will have nicer statistical or computational properties. We draw our inspiration from the large literature on estimating causal effects through covalent adjustment, which is currently the most common technique for causal effect estimation. Here we assume there exists a set of covariance Z which satisfied the so-called backdoor criterion, or the ignorability in the statistical community. If they satisfy the backdoor criteria, then the causal effect X on Y can be estimated by this Covalent adjustment. And there is a large literature on estimating this particular estimate. For example, we could estimate this expression directly by estimating this conditional distribution Y given XC, or the outcome regression. And then we plug in to compute the expectation. In a different form, something called the IPW. We rewrite the expression in a different form. And here the nuances is probability of X given Z. I believe they are known as the propensity score. So we estimate this probability, then compute this expectation. Now, in both these estimators, we require the nuances to be correctly estimated in order for the estimation to be correct. Also, for the estimator to achieve desired square root n consistency, we'd like the estimates for all the nuances also converge at square root n. So if the estimates are misspecified, then the estimation may not be correct. So that's known as the misspecification problem. And also, if the estimates for the nuances, they do not converge fast enough, then your overall estimates will not be able to achieve square root inconsistency. So why this is a concern? Because in recent years, when we are trying to deal with high dimensional complex data, we are often going to use machine learning models to estimate those nuances. For example, those neural networks, random forests, they are known to converge slower than square root. So then your estimators may not behave well. So in practice, we have the potential issue of model misspecification, in particular when the data generation process is complicated. And we have the issue of slow convergence, particularly if we want to use those flexible machine learning models. And the standard plugin estimators for the general causal functional estimates will suffer the same issue. To address this issue, double machine learning estimators have been proposed, called the double debiased machine learning estimator, or DML estimator. For this expression, we use a different expression. This is called the augmented IPW estimate. So if we use this expression, it turns out either one of PS given Z or probability Y given YZ, either one of those nuances is correctly estimated, then the overall estimate can be correctly estimated. So this is known as a doubly robustness problem. And further, if we use something called the cross-fitting technique, that is the training of the nuances and the samples for final evaluation. If you use two independent sets of samples, it's called cross-fitting. Then we may achieve something called the debiasedness property. So even if the nuances converge at a slower rate, like in this one quarter rate, then the overall estimator can still achieve the square root inconsistency. So the objective of this work is we would like to develop DML style estimators for any causal effects identifiable from a given causal graph. And we are going to assume that all the variables are discrete and all the conditional probabilities are positive. We will follow the recipe given by the work in Chernozyukov. The idea is to construct the DML estimator. You first construct the Neiman orthogonal score of your target estimate. So the estimator will be constructed using this score. And then we're going to use the cross-fitting technique to actually estimate the estimator. So a DML estimator constructed in this way achieves the debiasedness property. That is, it achieves square root n consistency, even if all the nuances converges in a slower rate. So that here is the general outline. So first, we study a special case of this problem. We consider a causal effects identified under so-called multi-outcome sequential backdoor criteria, MSBD criteria. We will derive Neiman orthogonal score for causal estimate under this criteria. And then we show that any identifiable causal estimate output by the IDP algorithm can be represented by a multiplication, division, marginalization of the MSBD estimates. We will call these operations the arithmetic combination. Now, once we establish that, we show that we can then derive a Neiman orthogonal score for the arbitrary estimate using the Neiman orthogonal score of the MSBDs. Finally, based on this score, we construct a DML estimate. First, let me review this MSBD criteria. So it's an extension of the sequential backdoor criteria. And the sequential backdoor criteria is the extension of the backdoor criteria to the sequential case. So roughly speaking, we say a sequential of Z variables satisfy the MSBD criteria relevant to a sequential of X variables and the sequential of Y variables. If all the non-causal paths between each Xi and Yi are blocked by Zi, conditioned on all the previous ones. So if Z satisfies such a criteria, then it can be shown that the causal effects can be expressed in this form. So I will call this MSBD adjustment form. And I'm often going to use this operator to define this operator as a shorthand to represent this expression. As an example, in this model, Z1, Z2 satisfy the MSBD criteria relative to X and Y. Oh, okay, the errors disappeared from this graph. So basically the order in this graph is Z1, X1, Y1, then Z2, X2, Y2. So that the direction can be fixed by this order. So in this particular graph, the causal effect can be expressed in this form. Here's another example. The causal effects of X1, X2 on Y can be expressed in this form. So we have derived a Neiman orthogonal score for this MSBD adjustment estimate. And the expression is given here. It basically consists of two groups of functions. The HIs expressed by this expression, and more details are here. So the nuances are those probability of Y given the previous one, probability of Z given the previous one. And the nuances for W are probability X given previous variable. And once we have this score, we can explicitly construct a DML estimator, which satisfies the doubly robustness property that whenever either the nuances in HI or the groups of nuances in WR are correctly estimated, then the overall estimate will be correct. And they have the debiasedness property. So that's the result for a special case when the causal effect can be identified by the MSBD criteria. I believe now is a good time to pause to answer a question.
Thanks, Jin. So let's see, currently nobody has raised their hand, but if there's anyone in the audience currently who has a question, you can just raise your hand and I'll unmute you. Okay, there's one question that we just got in Q&A. So we have one person asking, does this imply that you can also get the conditional average treatment effect estimate for any causal graph that is identifiable, or do you only get the average treatment effect?
So what we get is actually the effect itself, probability of y given to x. So once you have the distribution, then yes, I believe you can then estimate the average effect. So here all the effect identification, I'm talking about the probability of y given to x, so the distribution itself.
Okay, I have one quick question. This might not be a good question, but so are you also, the estimator that you construct, is it also efficient among all the identification strategies?
No, we don't have the statistical efficiency problem. No.
Okay. Thanks.
Yeah, that would be other desired property, but no. For the general identifiable causal effect, I believe that's still an open question.
Could I ask a short question about the MSBD? So this is a generalization of the sequential backdoor to a graph with hidden variables, right? Or okay.
Oh, I believe sequential backdoor also applicable to hidden. The generalization is in Y. The outcomes, standard sequential backdoor Y is assumed to be either a singleton or a group, basically. It cannot be split.
I see.
The generalization
I see.
is we can have Y1, Y2 split in the middle. So
okay,
that's the
thank
generalization.
You. Yeah, I see.
All right, thanks. I currently don't see any raised hands, so I think you can continue, Jin.
Okay, so next I will discuss the general case. That is how to estimate a causal effect that's identifiable by the ID algorithm. First, I will briefly revisit the ID algorithm. So some important concept used in the ID algorithm. First, the concept of C component. So a set of variables are set in a C component if they are connected by a bidirected path. For example, in this graph, we have V1, V3, V5 in one C component, V2, V4 in another C component. And we have the concept of C factor that's defined over C, QC. It represents the distribution of C under the intervention on all the other variables. So this is called a C factor. It turns out the joint distribution can be factorized into a product of the C factors over the C components in the graph. So this essentially generalization of standard Markov factorization into the model with hidden variables. And the basic operations we could do with C factors, we have if W is ancestral in the graph, then we may estimate QW from the QC. And in general, for any QH, which can be factorized into a product of C factors over the C components in the subgraph over H. And each of the C factors will be identified in terms of this C-factor QH. So based on those properties, a complete algorithm for identifying causal effect have been developed called the ID algorithm. So I will not discuss the ID algorithm. The basic idea is it recursively applies those C-factor operations. And in the end, it will either output an expression for your target causal effect, or if it's not identified, it will output a fail. Now, our observation is that for any given target effect, the ID algorithm actually output an expression which is an arithmetic combination, which means the product, division, and marginalization over a set of identified C-factors. For example, for this napkin graph, the ID algorithm will output this expression. It's in fact, this expression is obtained from this expression. So it's expressed as this is a C-factor over W, X, and Y. It's expressed as marginalization and then a division. So this is our first observation. Then we realize that all those identified C-factors used in the ID algorithm, they can in fact expressed as a MSBD adjustment form. So what we have done is we basically modify the ID algorithm. So we will call it DML ID algorithm, such that the output, the identified causal estimate is expressed as an arithmetic combination of the MSBD adjustments. For example, in this model, so basically each of this form is expressed in a MSBD adjustment, which I have defined previously. In fact, for this particular one, each of them is a backdoor adjustment. So MSBD adjustment in this case reduced to the standard backdoor. This is in fact the causal effect of R on XY with W as a covariance. The bottom one is the causal effect of R on X adjusted by PW. Now with this observation, given that we are able to derive Neiman orthogonal score for the MSBD adjustment, we try to derive a Neiman orthogonal score for the general expression for the any this arithmetic combination. So basically based using this property. So here, this phi mi represent the Neiman orthogonal score of the MSBD adjustment. So based on this property, we are able to develop a recursive algorithm. So given this expression, we develop a recursive algorithm that will be able to derive a score. So in summary, at this point, what we have is we have an algorithm. Given the target query and the causal graph, our algorithm will systematically derive a Neiman orthogonal score. Now, based on the score, we will construct a DML estimator. First, we have that here phi is the score we derive. Satisfy the property that it can be expressed as this function they're known as uncentered influence function minus your target estimate. So such that then the estimator can be constructed by computing the empirical expectation over the uncentered influence function. And then we follow the standard cross-fitting technique. So we split the samples into two halves, randomly split into two halves, use one half to estimate the, use one half to estimate the nuances and use the other half to estimate the empirical expectation. So that's the DML estimator we constructed. So the proposed estimator will satisfy certain doubly robustness property. That is, it will be robust with either one group of nuances are correctly classified or another group of nuances are correctly estimated. And we show that they have the debiasedness property. And also this estimator, as we shown that it works for any identifiable causal amount given a causal graph. As a specific example, for this napkin graph, the causal effect given in this expression can be expressed as a ratio of two MSBD adjustment, in fact, two backdoor adjustments expression. So based on this expression, now first we can derive the Neiman orthogonal score for each of M1 and M2 for each of these two expressions. And they are given here. In fact, they are in the familiar form of augmented IPW. And then based on the ratio form, we run our algorithm. We derive the Neiman orthogonal score for the causal effect, expressed in terms of the orthogonal score for the MIs. And here mu's are the expected value of those uncentered influence function. And the uncentered influence function itself can also be computed like this. Now for this particular estimator, they satisfy the doubly robustness property that the estimator would be correct if either the nuances for this, basically those are the nuances required for the standard plugin estimate, or the nuances for probability R given W are correctly estimated. And it satisfies the debiasedness properties. That is, all those nuances, even if they converge at N1/4 rate, the overall estimate can still achieve square root inconsistency. So we have run the simulated experiments to confirm these properties. We have simulated the debiasedness and compared our estimator. Our estimator is this blue line with the standard plugin estimator. And this is basically the estimation error. Here we are estimating the probability of y equal to 1 given x, then compute weighted average over x values. So that, and compute your estimation minus the true value, since this is simulated data. And this is when compare the debiasedness property. So we also simulated the double robustness property. First, we simulated to misspecify these nuances. Here we show the plugin estimator will not working well because plugin estimator actually using this nuance. But our estimator still works well. Now we also simulated what if the other one, the probability R given W is misspecified. This one, the estimator is comparable with the plugin because plugin is not using this nuances. So that's the simulation result. Okay, I think I should another time to pause and answer questions.
Currently,
so
there are no open
questions. The graph-based approach.
Yeah, currently there are no open questions. Younghan has answered all of them. Let's see what is If someone has a question, please raise your hand. Nope, there seem to be no question currently, so I think.
Okay, then I will move on to the second scenario.
Yeah, quick reminder. Sorry, you have around 10 minutes left. Sorry for interrupting.
What's that?
You have around 10 minutes left. Sorry, just a reminder of the time.
Yeah. Right on time. So in the first scenario, we have assumed we know the causal graph. So in the second scenario, we will consider purely data-driven situation. So we only have the observational data. We do not have the causal graph. So we are going to assume that we can run some causal structure learning algorithm, attempting to learn the underlying causal graph. While causal structure learning has been well studied, there's a large literature on it. Now, in general, it's known that given purely non-experimental data, if we don't make any other assumptions about the underlying causal mechanism, we will not be able to learn the unique underlying true graph. Instead, we are able to learn a Markov equivalence class of the underlying true graph. Basically, a set of graphs which have the same Markov properties or have the same or encode the same conditional independencies as the true graph. Specifically, we will consider partial ancestral graph, which provides a graphic representation of Markov equivalence class of graphs. And a pack could be learned from observational data by, for example, the FCR algorithm. So in this approach, we are going to assume we know the packs. Now, for your information, here are some example packs. So packs represent a group of graphs. So we have in the graph, we have those circles to represent structure uncertainty. So a circle here essentially means it could be either a directed error or bidirected. Also, those errors itself, they just represent ancestral relationship. So there is a lot of uncertainty. So they are group, they represent a class of causal. Then if we assume that we have the pack and we have the observational distribution, then the causal identification under this situation asks, is the causal effect uniquely identifiable from the distribution? So if it's not identifiable from the distribution, could mean that they are in the underlying, in the equivalence class, there might be different graphs which agree on PV, but they disagree on the causal effects. If they are identifiable, it means that in all the causal graphs in the equivalent class, they both agree on the distribution and agree on the causal effect. Now, this identification problem has recently been studied. And again, a complete if and only if identification algorithm have been developed, algorithm called IDP. For example, given this pack, the IDP algorithm will output this expression. Now here, we are concerned with the estimation problem. So given some arbitrary causal effects estimate output by the IDP algorithm, we would like to develop DML style estimators. So that's our goal. So what we have done here, I will not go to the detail, give a rough outline. So what we have done is based on the IDP algorithm, we have designed the algorithm which given a DAG, given a pack, given a target causal effect, it will derive a Neiman orthogonal score for the target causal effect. And based on the Neiman assortment score, we are able to develop a DML estimate. And we call our algorithm DML IDP algorithm. So the algorithm will satisfy the debiasedness property. That is, the estimator converges in square root n, even if all the nuances converges slower. Also, it satisfies a certain doubly robustness property. That is, the estimate is consistent even when a portion of the nuances could be misspecified. And I will show the property with this particular example. For this graph, this is the expression given by the IDP algorithm. And use our DML IDP algorithm, we have derived the estimator. And the detailed expression is too messy to show. So here I will show the double robustness properties. So double robustness properties basically says that our estimator will converge if either this one or this group is converged, and this nuance or this group of nuances will converge. Well, you can compare with the standard plugin, which requires all these groups of nuances to be converged. So that's the doubly robustness property. And also it satisfies the debiasedness property. Also, we have confirmed our results with simulation experiments over this graph. So we simulated a generated structure causal model, use it to generate simulated data. So here is the experiment on the debiasedness property. Compare again with the plugin estimator and our DML estimator. And see the plugin estimator, the variance is very large. So this shows the debiasedness property. Similarly, for the doubly robustness property, we simulated two situations. One is this one nuisance is misspecified. All the others are correctly specified. And it shows that the plugin estimator has trouble because this nuance is actually used in the plugin estimator. But our estimator is still okay. And we also simulate another situation. These groups are misspecified and all the others are correctly estimated. The plugin estimator also uses these two nuances, so they will have a problem. And our estimator is still relatively robust. Okay, conclusion. So we have developed DML estimators for causal effects identifiable given observational distribution that enjoys double robustness against certain model misspecification and debiasedness against biases in nuance function estimation. Specifically, I have presented the result on two scenarios. In the first scenario, we assume we are given the causal graph and the observational data. We have developed a DML ID algorithm, which will give a DML estimator for any identifiable causal effects given this causal graph. And we believe this is the first kind of result for the any identifiable causal effects. In the second scenario, we assume that we have a given data, we also have a peg a partial ancestral graph, which in principle could be learned from the data. So we call this the purely data-driven approach. Now, given data and such a pack, we develop a DML IDP algorithm, which will construct a DML estimator for any causal effects that are deemed identifiable given the pack and the observational distribution. Okay, this concludes my talk. Thank you. Okay. Here are some references.
All right, great. Dominic, are there any questions you'd like to raise?
No, I think Johan has answered all of them, or is currently answering them.
Okay, well, in that case, let's move on to the discussion. So, and then we will have a short time, hopefully, for questions after that. So, Ilya, feel free to take it away.
Can you see my slides okay?
Yeah.
Yes.
Great. Well, thank you, Jin, for a very interesting talk, and thank you for the organizers for giving me a chance to chat about this very interesting paper. So I got excited, made a bunch of slides. It's mostly, I'll try to go through them fast. It's mostly just history of ideas and some questions for Jin. And I wanted to acknowledge my colleague, so Eric Chetkin, who was very helpfully discussed the history of ideas on the estimation side with me. I just wanted to try to get that right. And Robin Evans and Thomas Richardson, who discussed the DML-ID algorithm with me. And one of the examples I'm going to discuss later is basically a very minor tweak of Robin's example. Okay, so this is a causal inference talk. In causal inference, we have these. This is sort of the simplest interesting model, the backdoor or the conditionally ignorable model. We have some covariates, a treatment and an outcome. We want the average causal effect, which happens to be identified by the adjustment formula or the G formula. And the interesting thing with causal inference is the target of interest is a scalar, but to get it, we need to estimate some nuisance models. And so two big questions in causal inference that were sort of both addressed by this talk is, the first is, under what circumstances is the target parameter identified as a function of the data? And question two, how do we get sort of a nice estimator if we have a low dimensional parameter with nuisance models? So just as a brief history on the identification end, this stratification or covariate adjustment formula is a very old idea. I'm actually not sure where it appeared first. It definitely appeared in epidemiology a long time ago. This was generalized to longitudinal data when you have time varying confounders, where we could sort of sequentially adjust to yield the G computation algorithm. This is due to Jamie's famous 1986 paper on the healthy worker survivor effect. Yuda Pearl, of course, has done an enormous amount of work on this problem, and he proposed that there are some counterintuitive situations where you have unobserved common causes of the treatment and an outcome where you're still identified, such as the front door criterion, and eventually proposed the do calculus as a general kind of deductive inference scheme for getting identification. Of course, Jin proposed the ID algorithm as a general approach to getting all identification, and this was eventually proved that this was indeed a complete algorithm. And there are lots and lots of extensions to conditional effects, selection bias, mediation, transportability, surrogates, and all sorts of things by lots of authors, including Jin and Elias, of course. And on the double ML estimation end, of course, this is all rooted in inference, in statistical inference and semi-parametric models, which is a very well-established area in statistics. So you could consult early books and papers by Bickel and van der Waart and Newey. The use of semi-parametric methods, in particular influence function-based methods, I think traces back to a paper by Robbins, Rudnitsky, and Zhao in '94 for a missing data problem. A little bit later, it was realized that there are sort of product bias properties of these estimators, and you get double robustness, or as I like to call it, 1 out of 2 robustness. I think it's more intuitive what that means. And this is discussed in a number of places in Sharfstein and Rudnitsky and Robbins, and in Robbins' comment, and in Robbins and Rudnitsky's comment in the late 90s, early 2000s. So a lot of this stuff with name and orthogonality kind of goes back to these kinds of product bias influence function based estimators from semi-parametric statistics. And indeed, using flexible nuisance models and cross-fitting has been discussed before as well by Jamie in the context of sequential decisions, by Eric and collaborators in the context of higher order influence functions, and by Mark Vanderlaan and Zheng in the context of targeted learning. Now, and of course, double ML paper, the famous paper by Chernozhukov and colleagues, proposed name and orthogonality conditions and the use of flexible ML to do inference on causal effects. Now, in principle, of course, any moment or score that satisfies these conditions can work and can be adapted into this double ML framework. But in practice, these moments or scores tend to be just influence functions. Now, Jin Tian and Barenboim developed a very interesting paper marrying semi-parametric estimation and graphical model-based identification. And so their contributions are an orthogonal score for what they call multi-outcome sequential backdoor, so MSBD condition, an orthogonal score satisfying name and orthogonality for any interventional distribution identified by the IDP algorithm, double robustness for these estimators based on these scores, and adaptation of these methods for post-selection inference. And the orthogonal scores, as far as I could understand, were obtained by a functional derivative version of the chain rule. So there are some questions posed by this work that I wanted to discuss, which is relationship to prior work, practical estimators, efficient AFs, what kind of robustness do we really get, and how do we incorporate model selection really? So the first question for Jin is, it seems, correct me if I'm wrong, that the functional that you get by sequential backdoor is just the G formula given by the G computation, although you have a graphical criterion, that's really what it is. And once you're doing influence functions, really it's the functional that matters, not the graph. And if this is true, the influence functions for these have been known for a very, very long time. I don't think this is really necessarily novel. And of course, once you fix the functional, the only relevance of the graph is for getting the constraints if you want to be efficient, because the graphs imply certain restrictions on the observed law, and you could project and get a more efficient IF. Okay. So, but maybe it's not quite the same as G computation. I'm not quite sure. All right. So if we want to derive an AF, it might not by itself lead to a usable estimator in practice, of course. So for example, even in the sequential backdoor case, we could have many, many, many treatments, and in which case we have to smooth because of the usual cursive dimensionality reasons. There is a very rich literature on the so-called structural models, where basically you impose smoothness on counterfactual quantities in a helpful way. And there are lots of papers on this. One of the early ones is by Jamie on structural nested models and marginal structural models from '99. In addition, it sort of seemed to me that, I think there was this bullet point that assumed that everything is discrete. And if everything is discrete, it seems like you have a parametric model, and the most efficient estimator or within a particular model is just the maximum likelihood plugin derived from a likelihood that Robin Evans and Thomas Richardson came up with in 2018. And, if everything is discrete, it's not actually clear what the AF buys you. It's certainly not efficiency, and it's certainly not robustness, because, you have tables in discrete cases. You're not really misspecified unless you're very high dimensional, in which case you have to smooth, I guess. So the second question is, can we say something about in what cases we actually get something usable in the kinds of cases the double ML paper was written for, which is sort of high dimensional continuous covariate cases. And there is some special case work on this stuff, but not for everything that the IDP algorithm does. Okay, so this was already, I think, addressed by a question. So I was going to ask about efficient AFs, and it sounds like the answer is this is not really going to give you the efficient AF, which is fine. It sort of seems like it might be hard to do in general graphs. That's been my experience, at least for me. If you have something that's equivalent to a DAG, then it's not very hard. Otherwise, it seems like it might be hard. So one question for Jin is, what can we say about efficient AFs beyond this, if anything? And again, for discrete data, we just do the plugin MLE, I think. So I think that's the efficient thing to do, unless I'm missing something. Okay, so let's talk about robustness. Robustness of an estimator can sometimes be obtained by looking at the bias of the estimator and the parameterization. So in the celebrated augmented IPW estimator that Jin discussed, we get double robustness if you have kind of a natural decomposable likelihood parameterization. Whereas if you use an alternative one, which is equivalently good in some ways, which is based kind of on Markov random fields, you don't actually get double robustness here. So it's a combination of those two things that get us robustness sometimes. And so the claims here that you always get 1 out of 2 robustness, and I wanted to sort of ask about that. So here is a graph. This is a slight modification of a graph that Robin came up with. So here we want to identify, we have 3 outcomes and 2 treatments, L1, L2, and Y are the outcomes, A1 and A2 are the treatments. Here we have to identify this, we need to deal with 4 districts or C components as Jin calls it. We have to kind of factorize into districts and then try to get each term using the IDP algorithm. And if we do that, this is what we get, unless I made a mistake. Notice that we don't actually get identification using G computation here because you have a front door graph as a subgraph, like A2, L2, and Y is the front door. So G computation won't work here. But if you look at each district term, you can think of each district term as a G computation functional, maybe with a sum in front. Okay, and I kind of gave names for some of the nuisance models here under the natural parameterization, where you just parameterize in the order, basically. Okay, and so if we just wanted one of the terms here, we get double robustness, and this is very well known for anything the G computation outputs. So this is kind of sequential backdoor. So it's very well known you get double robustness, and the models are either everything in the district or everything outside of the district. So one of those two has to be right. And so if you apply this to each term here, you see that you get double, kind of a disjunctive thing where you need 1 out of 2 model sets correctly. Okay, fine. So then we have to combine it. And if we combine it, we need to get each district right, or so it seems to me. And so you have an and of an or. And if you use distributive property of and an or, and you simplify a little bit, it sort of seems like you get this disjunction here of 3 things. And notice that 2 and 3 and 4 and 5 models always occur together. And so under a reasonable likelihood parameterization for this graph, it sort of seems to me that we get this kind of robustness. And each class of models occurs in exactly 2 places out of 3. And so it's not obvious to me how to simplify this to get double robustness because of this. Now, it may be that I missed something, of course, or maybe there is some weird trick, but I didn't see it. So the question is, what sort of robustness do we actually get from ID? If this is right, and maybe it's not, but it sort of seems like here we get 2 out of 3 robustness rather than 1 out of 2 robustness. 2 out of 3, of course, is not as good. And this does arise in other problems, like in mediation problems that Eric wrote about. And so question 4 for Jin is what's going on here with these examples? So the possibilities are, I made a mistake. That's, of course, possible. I only had a couple of days to think about it. And of course, this is Robin's example, not mine. I just tweaked it a little bit. So it's possible maybe you could group terms in some way I haven't thought of to get 1 out of 2. It's possible to use another likelihood maybe to get 1 out of 2. Or it may be that actually the target parameter bias for outputs of ID is complicated, and you don't always get 1 out of 2 actually. And it may have to do with how you have to combine terms from each district. Each district is 1 out of 2, but it's not clear if you always combine them, it stays 1 out of 2. Okay, so then the final contribution in this paper was what everybody calls post-selection inference. So you first do model selection, you learn the graph. Then you consult existing methods that tell you that in some circumstances, if you have an equivalence class represented by a PAG, everything in the class gives you the same functional for the effect, and then you run your algorithm there. And of course, most of the time this won't happen, but sometimes it will. And then you apply DML ID. And so the whole point, it seems to me, of using name and orthogonality is to get root n consistency, basically, and maybe robustness. But of course, everybody knows that if you use model selection, you don't get uniform consistency at any rate in general without strong assumptions. So if we apply this pipeline, it's not clear why we get root n consistency at the end, because we have a step that isn't consistent at any rate. So, and of course, there are uniformly consistent extensions that you could try, but then it seems that we should propagate uncertainty incurred from learning the graph with error. And this is post-selection, and to me, that seems really hard here. And also, one of the things that happens is you're using data. You're using the data to learn the graph, and then you're using the data to do something else. And you get weird correlations from that potentially. So another question for Jin is, can anything be said about actually getting root n consistency here in settings where you don't really want to treat the PAG as fixed? And I should say, this is not a criticism. This is a hard problem. And I myself have some prior work on this where we basically ignore this issue entirely, essentially. So I think it's understandable, but it is an issue, I think, and people do work in post-selection in statistics. Okay, so to conclude, very interesting work at the intersection of graphical model identification theory and semi-parametric theory. It would be nice to clarify a relationship to prior work and the robustness properties we actually get from ID. This brings to light really, really interesting and difficult questions that I think would be great to address and directions for follow-up work. And it is my hope that one thing I really liked about this paper is a synthesis of multiple areas that were previously separate in causal inference, and I really hope this trend continues. I think that's a great thing. Finally, I wanted to thank Jin for presenting this interesting work. This was great. This is some references on identification. This is a lot more references and estimation. I tried to be comprehensive. And this is some other stuff that came up in my discussion. And thank you. That's all I had. Hopefully I didn't run over.
All right, great. So let's have Jin maybe comment on if he has some.
Wow, that's a lot of tough questions. I
Sorry,
believe most of them
Jin.
are open, unanswered questions. I don't think we solved all those problems in these papers. And for your last point about doubly robustness, I believe we just borrowed this terminology. To my understanding, the robustness properties we get are indeed something like that. This group or that group or that group. So I guess that is, if you want it triply robust.
So,
yeah.
But the thing is that then you have to be very careful, because if you're going to get root n rates, then the reason you get n to the fourth for nuisances is because they multiply to get you n squared. But if you have triply robust things, I think it becomes a lot less obvious, or more than triply, like, like 3 out of 4, for example, then it's not obvious. In fact, I'm not sure this is a solved problem. Like, under what circumstances do you get a root n estimator? But it's definitely not like double ML, right? I think that's a little, I don't know if that's a good nomenclature for what's happening, because double implies 1 out of 2, which is, I don't think is what happens here. Or maybe it does, I don't know. I mean, I'm kind of open to the possibility that I made a mistake.
For the other questions, as far as I can remember, no, we don't have we don't claim any efficiency, no.
I guess the other question I had, one of those was, you assume discrete data. So why should we even not, why should you just not do maximum likelihood for discrete data, basically?
Well, first we are trying to consider high dimensional situation. And another possibility, this can be extended to allow some continuous covariance as far as to make sure the influence function well defined, I believe. So here to be simple, we just assume everything to be discrete.
And if the causal graph is, if we are considering the case where, everybody can hear me, by the way?
Yes.
Oh, yes.
All right. So yeah, for the case that the causal graph is given instead of enumerating the identifiability condition, then actually the graph itself imposes a lot of other constraints. So even if we use the plugin estimator for the very simple case, we cannot really assure that this is the efficient case. It depends on which kind of the model we are considering based on the graph, I think. So yeah, it's a different thread of the discussion, but yeah, I just want to make a comment on it.
All right. I think so. We're over time. So, but there's a question from the audience. But maybe then it's best. Oh, Dominic, you have.
Yeah, let's first wrap up and then we can unmute people.
Okay, great. So, so let's wrap up our official segment of the seminar here. Thank you all for being here and for listening to these wonderful presentations. Thank you, Jin, for presenting, and Ilya for a very insightful discussion, and Yonghan, thank you so much for a very nice discussion in the Q&A as well. All right, so just one more thing. So next week, we'll have a presentation by Limbo Wang from University of Toronto on causal inference on distribution functions. So we hope that you all join us next week for that. Thank you so much.
Thank you.
Thank you very much.